All right, so here we go. So 7.3, number 6. So I guess before we do anything, a quick reminder. So one of the important things from the video, or arguably the important thing from the video, is this. If an object is rolling, and when I say rolling, I mean rolling. Like, it can't be sliding. It can't just be spinning in place. It has to be literally rolling, okay? So if an object is rolling, it turns out that there's a super secret ninja shortcut you can use to calculate your rotational kinetic energy. And that shortcut is this. It turns out that your rotational kinetic energy is always equal to this magic number B times whatever your kinetic energy is. Okay? So, what is B? Well, remember, you guys, we learned about rotational inertia in that video, okay? And so the rotational inertia is, well, there's a big list of them on the back of your equation sheet here, right? Okay, so all of these little equations are rotational inertias. And if you look at them, they're all something times mr squared. Okay? So that something is your B. Okay, so you don't even need to calculate. At this point in the chapter, we don't even need to calculate the rotational inertia. All you got to do is know what B is and plug it in up here. Okay? All right, and then there's a shortcut you can take from there then. If you want, we can say, oh, well, suppose I want to find my total kinetic energy. Oh, well, that would be my kinetic energy plus my rotational kinetic energy, right? Okay, so I would go, all right, well, this thing is rolling down a hill. It's moving. It's got kinetic energy. Oh, it's rolling. And so the rotational kinetic energy is just this B times KE. All right, and so then what I told you is you could rewrite that as 1 plus B times your kinetic energy. Okay, so we've now got three types of kinetic energy, well, three different notations for kinetic energy. There's just regular old KE. That's the kinetic energy of a moving object. Okay? There's also rotational kinetic energy, which is the kinetic energy of a spinning object. All right? If it's rolling, it's got both types of energy, right? It's got kinetic because it's moving and rotational because it's spinning. Okay? And so TKE is just the total of those two types of kinetic energy. All right? So that's a quick 10-second review. Questions on that? Okay, so how the bleep do we use that to solve problems? All right, so let's take a look at number 6. So number 6 is about Sonic the Hedgehog, right? I think he shows up in 2 of these problems. So it says Sonic the Hedgehog is rolling about in his little world. He rolls over the top of a hill 30 meters high at 5 meters a second. He can be treated as a solid sphere. How fast is he moving when he's 12 meters up? Okay, so let's make ourselves a little drawing. Oops. So here's, all right, so here he is at the top of the hill. So the problem tells us that the height of the hill is 30 meters, and when he goes over the top of it, his velocity is 5 meters a second, right? And the question says, when he gets to the point at which the height is 12 meters, what is the velocity? So notice, this setup should look exactly the same as they looked when we did conservation of energy problems, right? It's all about height and velocity, height and velocity. Follow? Questions so far? I'm getting a lot of blank stares. Are we good? Okay, so, again, I'll come back to the why in a minute, but for now, let's just accept that the total energy at this point is equal to the total energy at this point. Okay? As we go down the hill, what kind of energy are we losing? GTE, right? And in exchange, we're gaining KE and RKE. Don't you agree that as he goes down the hill, if he's speeding up, he's also going to spin faster, right? Okay? So he's not just gaining kinetic energy, he's gaining kinetic energy and rotational kinetic energy. Okay? So my setup is going to be this. So let's call this point A, and we'll call this point B. So it turns out that the total energy at point A has got to equal the total energy at point B. Follow? So at point A, let's see, we're going to have GPE at point A. We're going to have KE at point A. And we're going to have RKE at point A. Okay? That all added together has got to equal the GPE at point B plus the KE at point B plus the RKE at point B. Cool? All right, so let's plug in some numbers and see what we can do. So the GPE at point A, well, that's m times 9.8 times the height. Notice I don't know the mass, so I'm just going to leave it as an m. Follow? Okay. Plus the kinetic energy, well, that's 1/2 the mass times the velocity, which is 5. Don't forget to square it. Good. Plus, I neglected to write down something that was super important. In order to find my RKE, I need to know what B is. So, answer a question.
Is it 2/5?
It is 2/5. How'd you know that?
Because on the back of the equation sheet, it says that. No, never mind.
No, you're good. It tells us something about Sonic. It says he can be treated as a solid sphere, right? He can be treated as a solid sphere. So just to be clear, there are two sphere things on there. There's a solid sphere and a spherical shell. So a spherical shell would be like a hollow sphere, like a basketball or something. Okay? So Abby's exactly right. So our rotational inertia then is whatever it is for a solid sphere. So 2/5 mr squared, right? So what's B? 2/5. Okay? So at this point, that's the only thing we need that equation sheet for, is to figure out what B is. Okay? So this then becomes 2/5, that's my B, times KE. So let me stop there for a minute. Does everybody see what I did? This is KE. This is 2/5 times KE. Follow?
So when you have the 2/5, you're just taking that value and ignoring the r squared.
I'm ignoring the mr squared, correct?
Yeah. Okay.
Yeah, well, and I went through that in the video why that's true, but basically what happens is the r squared and the omega squared combine to give you v squared,
Yeah. Also the
so they kind of cancel out, right? Yeah.
Wait, so could we have written that down, like 1 plus b in the parentheses? or
Yes, and so that was going to be the next thing I was going to say, is if you had wanted to, you could have combined this all. This is my total kinetic energy, right? So this mess here, if you simplify it, ends up giving you 1 plus 2/5 times 1/2 mass times 5 squared. So whichever of those two ways is easier for you to think about, either way works. So you're just going to have to sort of figure out what works best for you. Is that what you're asking?
Yep.
Everybody good? Yeah, AJ?
So it's way up higher in the back there. Oh, wait, never mind.
You good?
Yeah.
All right. Okay, so that's the total energy at point A. And that's got to equal the total energy at point B, which is m times 9.8 times what, 12? Plus 1/2 m times v squared plus 2/5 times 1/2 mv squared. These problems are tedious, I guess. Tedious isn't the right word. I don't know. A lot of numbers to keep track of. All right, are we good or no? Gigi, how you doing? You good? Why? How about you?
Yeah.
We good? Margo? Good? Yeah,
Why
Sarah?
can't you just do the 1 plus b times b before the 1 plus b?
you can totally do the 1 plus b thing. If that makes more sense to you, then do it that way. Totally. That was what
Keep it on
this
break.
guy, Ethan, asked. Sorry, I was debating Ethan or Evan. Sorry, Ethan. All right.
It's okay.
Everybody good? All right, so now simplify this. So let's see, the blue part. Well, first of all, does everybody see that the m's are going to cancel out? Every term here has an m, right? So if I divide by m, all of the m's go away. Okay, and so now if we simplify it, 9.8 times 30 gives you 294. Half of 5 squared is 12.5. 2/5 times that same thing gives you 5. Cool?
Yep.
Equals, over here you get 117.6 plus 1/2 v squared plus, so 2/5 times 1/2, don't the 2's just cancel out? So you get 1/5 v squared. Good or no? Yes? No?
Yeah.
Blank stare? All right. Okay, so this top mess up here gives you 311.5, I think, if I remember right. Equals 117.6 plus, and so here, I don't care if you do fractions, I don't care if you use your calculator, but 1/2 plus 1/5 gives you 7/10. So 0.7 v squared, or you can write it as a fraction, whatever, and solve it. Okay, so you subtract, square root, solve it, and you get, what does it give you? Anybody know offhand? Hi, well, wait a second. That will give me a chance to drink some cold coffee.
16.6.
Hmm?
16.63.
16.63?
Yeah.
Is that right? Yeah. Anybody confirm that? Is that right? We're good? All right. Questions on what I did there? Okay, and if you like the 1 plus b thing that I did in the video, that it's the same thing, right? This is, yeah, it's not, it's the same thing. All right, cool? All right, should I run through 5 real quick? Yes? Okay. All right, so let me stop this. I'm going to throw this on the website.